All right. Our target 5.7 mastery learning objective says I can calculate a 95% confidence interval for a sample population and a data set to compare sample statistics and population parameters. Okay. So, what that's going, the first thing we have to look at is what is a confidence interval. And a confidence interval, we're only going to be doing 95% confidence intervals, but again, if you take like AP stats, you could be any percent confidence. Okay. And what a confidence interval is in this case 95%. 95% of samples will have a mean or a proportion, depending on if you're looking at qualitative or quantitative, within this interval. So 95% of samples will have a mean or proportion within this interval. So our formula for qualitative is, right, it's an interval, so we use interval notation. Interval notation is parentheses, right, and it's between this and then that. For qualitative, remember, qualitative uses the p-hat, so it's p-hat minus your margin of error. And then your other number is p-hat plus your margin of error. Similar for quantitative, but instead of having p-hat, we're using x bar and x bar. Again, bar is actually what you call that, x bar, instead of p-hat. And then x bar is just your sample mean. Okay. So both of these are kind of like the middle, right? The proportion's like the middle, your mean's like the middle, minus your margin of error or plus, and then plus your margin of error. Okay. So similar, but again, slightly different. And again, remembering that these two margin of error formulas are different. So that's really where the big difference in these problems comes from. All right, let's look at example 1. Lindsay has heard complaints that the cafeteria lunch line moves too slowly. The dining services coordinator assures her that the average wait time is 6 minutes. The students think it is much longer. Lindsay selected a random sample of 40 students and measured their wait time. The mean wait time is 7.3 minutes with a standard deviation of 2.821 minutes. Okay. So, is this qualitative or quantitative? Right? Again, my answer to the question is like, how long did I wait? I waited 7 minutes. It's a number. So this is qualitative. Nope, just circled the completely wrong one. This is a number. It's quantitative. Okay? So we're going to use our quantitative margin of error formula. Right, 1.96 times s over square root n, where s, remember, is our sample standard deviation. Her sample is a standard deviation of 2.821. And then our n is our sample size, and she selected a random sample of 40 students, so our sample size is 40. So that's 1.96 times 1 over the square root of 40. what am I doing? Sorry, 1.96 times 2.821. Didn't put the 2 in. Over the square root of 40. And we get 0.874. I rounded that correctly, 0.874. Yeah. And again, we use thousandths a lot, but sometimes it's what makes sense. So now I want to do the 95% confidence interval. And again, our confidence interval is for a proportion, or for a data set, is x bar minus your margin of error that parentheses, and then 2 x bar plus your margin of error. Okay. And that's going to be, well, our x bar, that's our mean, right? Their mean wait time was 7.3, and our margin of error, we just calculated that to be 0.874. So we have 7.3 minus 0.874 and 7.3 plus 0.874. We get 6.426. At 8.174. And 8.174. Okay. So once you find your margin of error, this adding on that confidence interval is pretty easy, right? You're just subtracting it and then adding it. So what is the meaning of the 95% confidence interval? So again, what that confidence interval means, and this really is kind of like a memorized explanation, I guess, is 95% of samples of size, and then we have to say whatever this size was, right? It only works if the samples are all the same size. So there's, I don't know, 3,000 kids in this school, right? I'm going to take this random 40. Now I'm going to choose another random 40. Now I'm going to choose another, right? No matter how many times I choose a random 40 students and redo this experiment, 95% of those samples will have a mean wait time between these two numbers. So 6.426 minutes and 0.174 minutes. Okay. So, again, 95% of all of our samples are going to have a mean wait time between those two numbers. So what can we decide? Well, our lovely dining services coordinator said that the average wait time is 6 minutes. Well, less than 5% of our samples would have a wait time of 6 minutes, right? That seems unlikely that that is actually true. So what we say is, who is this? Who are we talking about here? Who did this? Lindsay. Lindsay's research that she just did does not support the claim that the average wait time is 6 minutes. Okay, so we either support or we don't support. We can never really prove anything. We're never proving it's true or disproving it's true. We either say, yes, I support this claim, or no, I don't support this claim. So Lindsay's research supports this claim. Or does not support this claim because the 6 minutes is outside of this interval, right? It'd be to the left of it. Okay. All right, let's look at another one. The National Academy of Science reported in 1997 that 40% of research in mathematics is published by U.S. authors. The mathematics chairperson of Loyola University wishes to test this percentage is now higher. He surveys a random sample of 130 recent articles published by research journals and finds that 62 of these articles have U.S. authors. Is this qualitative or quantitative? So what I'm actually asking is, does this have a U.S. author? That's yes or no, right? There's no number there in the actual question that we're asking. So this is qualitative. So we're going to use our qualitative margin of error. 1.96 times our square root of p hat times 1 minus p hat all over n. Okay. And in this case, our p hat, right, our proportion, well, it says 62 out of the 130, right, had U.S. authors. I will reduce that to 31 over 65. And then you don't have to reduce it. I sometimes find it easier for typing in, but you could just type in the 62 over 130. And then our n, right, well, they are a random sample of 130 articles. Plugging everything in, we have 1.96 times our square root of, well, p hat, again, is that 31 over 65 times 1 minus 31 over 65 all over 130. I'm going to make that a little bigger so that we know that 130 is also under the square root. Typing it all in, 1.96 lots of fractions, right? So we have 31 over 65 times 1 minus 31 over 65. Put that as a fraction. All over 130. So I get about 0.86 is our margin of error. So now our confidence interval for qualitative, remember, is p hat minus our margin of error and p hat plus our margin of error. Here I'm going to get our p hat as a decimal now. Right. Remember, when you want a decimal on these calculators, if you hit Control then Enter, it'll give it to you as a decimal. I'm going to round to the thousands place, 3 decimals. So 0.477. And our margin of error we just found over here is 0.86. That seems really off. Did I miss a 0 somewhere? 0.086. Don't forget zeros. Sorry about that. 0.086. Okay. So then, plugging everything in, I'm going to have p hat, so 0.477 minus 0.086 and 0.477 plus 0.086. Well, 477 minus 0.086 is 0.391, and 0.477 plus 0.086 is 0.563. So 0.391 to 0.563. So now, what is the meaning of the 95% confidence interval? Well, 95% of samples of size, this one had a size of 130, will have a sample proportion, right, because we're not talking about mean anymore, between, I'm going to put these into percent, 39.1% and 56.3%. All right, so if I took samples, 130 but an infinite number of 130 samples, right? 95% of those will have, when I find what proportion have U.S. authors, 95% of those proportions will be between 39 and 56, right? So that's where I would expect my actual sample proportion to be. So what can we decide from this? Well, the National Academy of Science reported that they said 40% of research is published by U.S. authors, and 40% does fall in this. So this research supports the claim that 40% of journal articles are written by U.S. authors. All right, so most of these words I'm just copying down from like the question, right? Right, but it's the research either supports or doesn't support the claim and then whatever it's talking about, right? Okay, we're going to do one more. So a lot of times you'll see the question like this. It won't be broken down into those different parts. Any basketball fan knows that Shaquille O'Neal had difficulty shooting free throws. Over the course of his career, his overall free throw percentage was 53.3%. During one off-season, Shaq worked with a coach on his free throw technique. During the next season, Shaq made 26 of 39 free throw attempts. Test the claim that he improved his free throw shooting. So this is, right, we have to decide if this is qualitative or quantitative. So what's the question that it's asking? Well, either made his free throw or didn't make his free throw, right? Made or didn't make. That's qualitative. It's not a number there, okay? So this is qualitative. So I'm going to first start with my margin of error formula. So P hat equals, well, he made 26 of 39 free throws. So P hat is 26 out of 39. Our sample size is 39. So then this equals 1.96 times 1.96 times the square root of 26 over 39 times 1 minus 26 over 39 all over 39. So I have 1.96 square root, lots of fractions, 26 over 39 times 1 minus 26 over 39. Right, so we get 0.148. Now that we have our margin of error, we need to find our confidence interval, right? And our confidence interval is going to be P hat minus our margin of error, and then P hat plus our margin of error. So P hat is that 26 over 39, which as a decimal is 0.667. And then our margin of error, that was supposed to be an M, is 0.148. Okay. So we're going to have 0.667 minus 0.148. Is he going to put parentheses there? It's not. Comma, 0.667 plus 0.148. Well, 0.667 minus 0.148 is 0.519. And 0.667 plus 0.148 is 0.815. Okay. So, 95% of samples of size 39 will have a sample proportion between 0.519, we're going to write that as 51.9%, and 81.5%. Okay. So his overall free throw percentage was 53.3%, and it does fall in there. Okay? So he did better, but what we say is he didn't do statistically better. Okay? It might have been a good season, but it doesn't really mean that he really improved. So this data does not support the claim that he improved, right? All right, that is it. It's a lot, I know. It's a lot of writing. Sorry for the longer video, but I will see you guys tomorrow.